The $11 billion fix to the U.S. energy crisis, HVDC. If you look at a map of the United States power network, it looks like a single, unified machine. It looks like an unbroken web of energy stretching from New York to California. But that is a complete illusion. The American electrical grid is actually broken into 3 completely isolated islands. These 3 grids do not talk to each other. They operate independently, governed by different authorities, and subjected to completely different macroeconomic stressors. If a massive winter storm knocks out power plants in Texas, the Eastern Grid, which might have thousands of megawatts of excess idle capacity sitting just across the border in Louisiana, cannot simply send power to save them. The infrastructure physically does not allow it. For decades, this fragmentation was an accepted engineering limitation. But in the age of hyperscale AI data centers and violent weather disruptions, these grid borders, known as the seams, have become the most dangerous vulnerabilities in the global economy. Today, we are going to look at the engineering of the Great Divide. We will break down why you cannot simply plug an AC wire across the border, the deep physics of high-voltage direct current converter stations, and the massive, multi-billion-dollar megaprojects currently being built to act as the living bridges of the modern world. Both the eastern and western grids operate on a strict frequency of 60 Hz, but they are not synchronized. Imagine 2 massive gears spinning at the exact same speed, but the teeth of the gears are slightly out of alignment. If you try to smash them together, they will shatter. If you build a standard, high-voltage AC transmission line and connect the eastern grid directly to the western grid, the out-of-phase power would collide violently. It would trigger catastrophic fault currents, instantly blowing out circuit breakers, detonating power transformers, and cascading into a blackout that could take down multiple states. Because of this phase mismatch, power cannot naturally flow across the seams. This isolation destroys economic efficiency. The Midwest might be generating massive amounts of cheap, renewable wind energy in the middle of the night, while states on the East Coast are burning expensive natural gas to keep the lights on. The energy is trapped. The solution to this bottleneck is one of the most complex feats of modern engineering: high-voltage direct current, or HVDC. We often think of transmission lines as mere wires, but in reality, they have to function as living bridges, intelligently managing the flow of capital and energy across isolated regions. HVDC allows us to bypass the synchronization problem entirely. At the border of the grids, engineers build massive HVDC converter stations. When out-of-phase AC power from the eastern grid enters the station, it hits a wall of advanced power electronics. These solid-state valves take the alternating sine wave and forcefully flatten it out, rectifying the power into a pure, flat line of direct current. Direct current has no frequency. It has no phase. Therefore, it cannot clash with the grid on the other side. You can pump thousands of megawatts of DC power across the continent with virtually zero line losses. When it reaches the destination grid, a second converter station takes that flat DC power and inversions it back into AC power, mathematically perfectly matched to the exact phase of the receiving grid. These HVDC systems aren't just dumb pipes. They are the ultimate grid stabilizers. They can precisely control power flow in either direction within milliseconds, providing synthetic inertia and voltage support to whichever grid is under stress. For decades, HVDC was too expensive to deploy at scale. But the explosive demand for power has shifted the macroeconomic calculus. Institutional capital is now funding massive private sector transmission lines to stitch the country together. Take the Grain Belt Express. Slated for construction in 2026, this is an $11 billion, 800-mile HVDC megaproject. It is designed to act as a massive, high-speed energy artery, picking up 5,000 megawatts of cheap power in Kansas and shooting it directly into the heavy load centers of the Midwest and the PJM interconnection. And the economic implications are staggering. By sharing capacity across regions with non-coincident peak demands, meaning the wind blows in Kansas when factories in Indiana need power the most, projects like this are projected to generate over $50 billion in energy cost savings. When you combine the Grain Belt Express with other massive pipeline projects like Sioux Green or the Three Corners Connector, you are watching the physical reorganization of the American economy. Capital is realizing that owning the power plant is no longer the most lucrative play. Owning the bridge that connects the markets is where the true generational wealth is secured. Over the course of this series, we have mapped out the harsh physical realities of the American energy crisis. We've seen how regulatory bottlenecks and hardware supply chains are fundamentally altering institutional commodity markets. But the grid is not static. Through heavy engineering and massive capital deployment, we are building the living bridges necessary to support the digital age. The isolation of the past is slowly being stitched together by advanced silicon and high-voltage direct current. The rules of energy economics are being rewritten right now, in real time. If you want to continue tracking the exact intersection of heavy infrastructure, grid reliability, and macro market shifts, make sure you are subscribed to USA Grid Mechanics. Thank you for joining me for this first major series. The real work is just beginning. Until next time.